Hi everyone. We are continuing our comparison of SN1 and SN2 mechanisms in substitution reactions, and this is part 2. If I could get through all of these other features of SN1 and SN2, for instance, stereochemistry, how the type of alkyl halide can affect the rate, solvent effects, then we'll be able to put everything together in the next video. So why don't we just go ahead and jump right in. I will assume that you viewed the previous videos on Unit 7. In particular, I think Part 1 was number 07D20. Okay. And that's where we introduced SN1 and SN2 and looked at a couple of mechanisms. Let me just make sure this is focused properly. Oh boy. Oh, there it is. Sweet. Let us, I think last time I started with SN2 because it's the easier of the two mechanisms. Why don't I do SN2 again? Start with that. So we're going to look at stereochemistry, because depending on whether you're doing an SN1 or SN2 reaction, you could have consequences for any chiral carbons, especially chiral carbons that are attached to the halide. And we'll start with SN2. With SN2, thus far, we saw that if you have a very good nucleophile, what you see is you get the attack and the leaving group leaving at the same time. So you can probably state it as the nucleophile kicks out the leaving group. Remember, in our analogy, the orange striped cat is aggressive and it kicks out the gray cat from the bed, from the the cat bed. Let me just remind myself what that looks like. So SN2, do you remember what SN2 is? Is it the top row or is it the bottom row? SN2 is, see, this is where the leaving group leaves, and that's the rate determining step when the leaving group leaves, and you require 2 cats in this step. In contrast, SN1 is the leaving group leaves here, but you only require 1 molecule because the nucleophile is just hanging out and waiting for the leaving group to leave. Okay, enough about that. That was review. Okay, so it kicks out the leaving group. So what I'm concerned about is a molecule such as this. And I'm going to put some stereochemistry, Br. And the nucleophile, let's make it a good nucleophile. One of our other good nucleophiles is the cyanide ion, and that looks like this. Both atoms have the lone pair, but the lone pair of this carbon makes it anion. Okay, you know how to figure out formal charge. So that carbon is negative, and we get a substitution reaction. But the mechanism is this. Remember, the mechanism is only one step, and you go from right to left, you hit this carbon. So the orange cat sits on the bed, and they kick out the gray cat. I'm not drawing the molecule just yet, because what I want to do is I want to look at the stereochemistry. And how do I want to view this? If I view it like this, should have practiced before I started this. Okay, how about this? Oh, I know what to do. So we'll have the methyl group here, the ethyl group here, Okay, here's your dot. And the bromine, so I'm just rotating this molecule. And the bromine is wedged towards us. And what's away from us? Away from us is the hydrogen. Okay. The thing is, this nucleophile is coming in at the same time the bromine is leaving. But the bromine is, as we can see, mostly on the right-hand side, the way that I drew it. So really the best approach for the cyanide is from the what's called the back side. So I'm going to draw the cyanide on the left, and I'm going to have it come in this way. Okay, and you know with an SN2 reaction, you get the attack and the leaving group leaves at the same time. The nucleophile kicks out the leaving group. I want to make sure that I'm doing this right. Okay, so what happens here, and admittedly I didn't draw this the best way, is that you have your nucleophile now on the left, and we have it here. And we have a bond to that dot. And what's happening here is that you're actually, it's called inversion. It's almost as if you have like a gust of wind underneath your umbrella, and the umbrella inverts. So we're going to push these bonds to the right. Okay, and man, let me think about this really carefully because I don't want to mess this up. The hydrogen is now here, and actually this cyanide is wedged. Okay, and that's called inversion. And where's the bromine? The bromine, well, becomes a bromide, and it's on the other side. I'm going to make sure that the stereochemistry did what I wanted to do, because what I'm thinking it's doing is that this comes from what's called the backside attack. And we get inversion. Inversion of the stereo center. Now, does that guarantee that if we start with R and we get S, or if we start with S we get R? Not exactly. It just depends on the priorities, right? But it looks like in this case the bromine is the highest priority in this molecule, and then when we replace it with a nucleophile, this group here, the cyanide group, is now the higher priority. Oops, I know I'm missing this. Right there. Okay. Whew. So I gotta make sure in this case that the stereochemistry did change from R to S or S to R. This was absolutely the hardest way to draw this molecule. I should have drawn it a separate way, a different way. But let's see if it still inverts, right? Sorry, that was covered up. Inversion. So if I take a look at this molecule of Br, ethyl, methyl, clockwise. So this is R. And then this one is, thank you, it goes from the nitrile, or you could think of it as a cyanide group, to the ethyl to the methyl. So this one's actually going counterclockwise. So this is S. What should I have done? Maybe I should have done this. I should have just kept it like that. And then when the cyanide does backside attack, okay, when you draw the mechanism, it doesn't really matter how you draw the arrows. I mean, whether that arrow is coming from the top or the bottom. But the way you draw your final product, you have to indicate that there is inversion. And the inversion simply is the cyanide came from the back. And you could draw it like that. And I guess in this case, this is R. And in this case, cyanide is priority number 1, priority number 2, priority number 3. It looks R, but since H is pointing in the wrong direction, you take the opposite. So it looks R, but it's actually S. And so these two are identical, and these two are identical. I just drew it really so bad. I want a second shot at this. I should have drawn this. I should have drawn the BR straight like that. And then, what should I have drawn? I should have drawn this methyl group like this. Okay. And this alpha group like this. And then the hydrogen, there we go, like this. Okay. And let me just double check. So that's still R. Okay. So now do you see, hopefully, the inversion? If I have the cyanide like this, coming in from the back side of the bromine, and this kicks out. Okay, your turn. What do you expect? You expect, I'll start us out, you expect the nitrile group to look like this, straight line, and there's your dot. Just imagine now all of these bonds inverting. Alright? If you want to pause the video. Okay. So, when this inverts, now we have this. This wedge is still this wedge, but now it's pointing a little bit to the right. And this dash is still dash, but now it's pointing to the right as well. That molecule is definitely S. Oh my goodness, that took a long time. Let me zoom out. Okay, so again, we are concentrating in stereochemistry. We just did SN2. And the better picture to show the inverted umbrella is this one right here. So we're going to think of this as an inverted umbrella. It's hard to see at first, but do you see how, it's kind of covering to the left, and then when a gust of wind hits it, it flipped over, right? And now it's covering, the umbrella part is covering to the right. You could get rid of this if you want, but this still is true. It's just a little harder to see the way that I drew the bromine. Okay. Ultimately, if you think you did an SN2 reaction, then you gotta draw an inverted product if your carbon that has a halide is a stereocenter. Okay, if it's not a stereocenter, it actually wouldn't matter. Imagine if this was an alpha group, right? You wouldn't put wedges and dashes because that carbon is no longer chiral, and you wouldn't be able to draw wedge or dash drawings on this product either. You have to have this chiral carbon on the carbon that's being attacked, But let me show you for SN1, because SN1, you notice that the cat doesn't do backside attack. It's actually waiting, and you form some type of intermediate. Do you remember what the intermediate was for an SN1 reaction? For an SN1 reaction, you go through the carbocation. And we're going to use a poor nucleophile and a crowded alkyl halide. Okay. And we'll make it chiral, so we could do a apples to apples comparison. But I want to make it really crowded. I'll make it tertiary. Oh boy. Here we go. Let's have this. And I need to make it asymmetrical. So how about that? And here's your bromine, and I need to make it tertiary. So here's a methyl group up here, and here's an ethyl group. So you understand that this carbon actually has a chiral carbon in the center. Okay, and I didn't want to make this hydrogen because I want it to be tertiary. If this was a hydrogen, then that carbon would be secondary because I want it very crowded. And then next I want a poor nucleophile. In the poor nucleophile, I'm going to use methanol. It's poor, right? Because it's neutral, and again, this is tertiary. But I'm trying to hedge towards making this an SN1 reaction. Okay. It goes through the carbocation. So remember SN1? And I know with mechanisms you normally don't draw wedges and dashes, but I want to prove to you that the stereochemistry of the product actually is a mixture of both R and S. Because what happens in an SN1 reaction is the gray cat leaves on its own. And we have something like this. Look what we have. I'm going to make this planar. Why? Because remember, SN1s go through a carbocation. What do you know about carbocations? Trigonoplanar. sp2, hybridized, flat, 120 degrees. All of those synonymous with each other. Remember what happens when you have a carbocation? The incoming nucleophile can come from the front or the back. 50-50. You can start to get racemic mixtures. So we can continue the mechanism. Let's draw this methanol. I'll draw it backwards. I'll draw it backwards because I want the lone pair to be closer to the carbon. Okay. Try to make it clear for your grader. Okay. But the thing is, this methanol can come from the front of the paper or behind the paper, which is underneath the table. And we get a mixture. How do you want to draw that mixture? You could draw it like this. So if the methanol comes from the front, the methyl group goes to the back, and we have, so don't forget that everything comes with a nucleophile, and we get a plus charge here. Remember with neutral nucleophiles, this is Nu, with neutral nucleophiles, typically you're going to have to remove the H at the end to make this neutral. But before we do that, what was the other enantiomer? The other enantiomer looks like this, where the methanol comes in from the back. And we have that. Oh man, you don't see that. And we have this. And the methyl group now is wedge. Okay. So these are enantiomers. They're not the final product. Oops, sorry about that. Enantiomers. I'm not going to deprotonate both of them. I don't want to waste that much time. But let me deprotonate this one. We could deprotonate with the Br-. And we have this. So we have a methoxy group as the final nucleophile. This is the thing that substituted out the bromine. So this is our starting material, and we kick out the bromine, and we added the methanol and took off the hydrogen. But if we did the deprotonation on this molecule, which does happen, look what we have. we now have the enantiomer. So this is called, as you know, racemic mixture. But also, what we can say in this case is that SN1 reactions can lead to, it's called scrambling. It's called scrambling because we started out with a pure chiral carbon. This looks like it's S, and then we get R and S for the final product. Okay, so in contrast, you have the inversion right here, one product, and here you have scrambling. Both of these have chiral carbons on them. Okay. So let's do another example. Let's try this. Chlorine. And I have to make this chiral so we can see the consequence of either inversion or scrambling. So here's a methyl group. And I gotta make this asymmetrical. So what can I do to do that? Let me add an OH group up here. Okay. So I'm going to add a weak nucleophile or a poor nucleophile. Water. This will be an interesting reaction. Imagine that you make the carbocation here, right? And then imagine that water comes from the front and the back. Oh, maybe before we do that, what would I do on an exam? I would, on an exam, I would say this is a poor nucleophile. On the exam, I would say this is tertiary. My conclusion for this is I expect SN1. That's the mechanism that I expect. And with SN1, you know you get scrambling. So to show scrambling, okay, do you realize that if water is your nucleophile, your ultimate group that's substituting is an hydroxyl group, an OH, because you want to get rid of that second hydrogen, or else this oxygen would be positive. But because we start out with a flat carbocation before the attack, the water can attack 50-50 front and back. Okay. That would be the answer, the correct answer with stereochemistry. If you conclude that this is SN1, you have to visualize that your intermediate is this. Flat. F-L-A-T. Okay. And that's why the water can come from the front or the back. And you get scrambling. Scrambling. Let me do one more SN2 example real quickly. Let's see if I can think one up. How about this? Okay. Let me put a terbutyl group here, or a crow's foot. I'm going to pick a good nucleophile, NaN3. Alright, so it's again your responsibility to be able to interpret this correctly. And how do I want to interpret this? I want to interpret it as the nucleophile being N3 minus, and it's good. It's a strong nucleophile. How do I want to interpret this? I want to interpret this as secondary. It's a little bit crowded. It's more crowded than primary, but it's definitely not tertiary. It's less crowded than tertiary. So with a good nucleophile, we can go ahead and have a direct attack. What these two pieces of information are indicating is that we're going to go through an SN2 mechanism. For SN2, you have inversion. The cat comes from the back side and kicks out the gray cat. And you get one stereoisomer. And you could indicate that just by drawing your nucleophile coming in from the opposite side. Remember, this was called backside attack. It doesn't mean that it always comes from the back. It always means that it comes from the opposite side, the back side of this bond. So if your halide is a dash, the nucleophile will attack wedge on the opposite side of dash. Now, you just got to be conscious of the fact that this, you can only see this or observe this happening if you're doing your reaction on a chiral carbon. It wouldn't have mattered whether it's wedge or dash if this wasn't chiral, if this was achiral, right? Can you imagine if it was achiral? So something like, let's say we just have that, two methyl groups. Well, your product you think would be this. But that's identical to this. So it doesn't make any sense to draw wedges and dashes because these two are identical. Right? This one's symmetrical. So both of these are achiral. This one is not. Right? The mirror image of this would be different. But we're not going to draw the mirror image. We're only going to draw the one stereoisomer that comes from the inversion of this alkyl halide. So that was a little bit longer than what I had expected. Let me see if I can get through speed of, let's start with an SN2. If you think that you have an SN2 reaction, what have I always done? I've tried to avoid it being very crowded, because if the cat is coming in at the same time that the gray cat is leaving, so the orange cat is forcing out the gray cat, you want this carbon to be very uncrowded. So in terms of speed, primary alkyl halides are faster in SN2 reactions than secondary than tertiary. That is the trend. And then for SN1, it goes to the carbocation. Oops. And we know that carbocations are more stable when they're tertiary. So tertiary alkyl halides will go faster than secondary, will go faster than primary. And this is actually a very common lab that most organic 1 professors do. Oops. Oh, let's put here lab. Okay. Because you could time these reactions with a stopwatch, because for these types of reactions you typically make a salt. And you just wait until you see salt, and that's when you know that the reaction is almost done. I know that was a little bit quick. This speed of the SN2 is based on crowdedness. The less crowded, the faster. This one is based on the stability. So the more stable the carbocation, the faster in an SN1 reaction. Okay. I'm going to stop there. We didn't get through solvent effects. So there will be a part 3 comparison of SN1 and SN2. Maybe in part 3 I will do this. I will review this a little bit slower. So this isn't as confusing as I think it is right now. Okay, so I'll see you in part 3 for SN1 versus SN2.